So remember again, power is the probability that we will be able to detect a significant result when it really is there. And so if we were to think about quantifying this, again, just like the p-value, it's on a scale of 0 to 1, right? Where a 1 means there's a 100% chance that I'm going to find that significant result. That's always dangerous because it just means you're calling every result significant. Typically, you'll see people using a power value between 0.8 and 0.9. So a 0.9 means that you would have a 90% chance that you will find a significant result when it is actually there, but still a 10% chance that you might miss a significant relationship. The question that I always get when I'm consulting with people who are doing analyses is, well, how many observations do I need? What's my required sample size? Right? They know that larger sample sizes are the way to keep their power of their test high, but they don't want to have to collect everything, right? So they want to know, well, how much do I need to collect to maintain that power? So really, it's all of these things that determine what your required sample size is, right? It's the effect size, right? How extreme is that difference or how strong is that relationship? It's our type 1 threshold, type 1 error rate threshold, that p-value, right? It's the power level that we're trying to get, usually around 0.8, and it's how much variability there is within the population. We've mentioned that these two are fixed, right? The population is what it is, and you can't change that, so we don't want to worry so much about those. We talked about not necessarily wanting to change our p-value, but we need to maintain this. So we need to figure out what sample size we need to maintain that without having to give up that. So let's think about this in terms of how it really would impact our required sample size. We'll start down here in the left-hand corner. If you have a really small effect, in other words, what you're looking for might be hard to detect, that means you're going to need more observations, right? But if you have a huge effect going on, then you probably won't need that many observations. That one's pretty straightforward. Okay, variability is similar. If you have very little variability in your population, it means you probably won't need that many observations to be able to see what it is you're looking for. But if there's a huge amount of variability in that population, so the data is sort of spread all over the place, it's going to be much harder and you're going to need more observations to pin down that true population mean and standard deviation. Okay. For our p-value, if we want to have a very low p-value, in other words, we want to set that threshold for the probability of making a type 1 error low, that means we're going to have a lot of observations. Right? But if we're okay with having a p-value threshold of say 0.1, then we wouldn't need as many observations. Right? Power. For maximum power, if you want to raise that power level, you need more observations. Are you okay with lower power? Then you can have fewer observations. So it's really how are we altering these that are going to determine our required sample size based on a given effect size and variability within the population. There are different power calculations for different inferential tests, but even still, those are educated guesses. And that's primarily because we don't know for sure exactly what the variability is in the entire population, right? Or what the effect size is we're looking for. We can estimate it. So still, this is always just an educated guess. So there are formulas. We can use the one sample z-test as an example for a power calculation, trying to figure out the number of observations that you would need. So we can do this out by hand, or we can just go into JUMP and let JUMP calculate this for us. And I think this is actually easiest if we use an example. So let's imagine that we have this medical study, right, where they have a new pill, a new sleep aid that's going to help people who have chronic insomnia sleep more. So the response variable that we're testing, right, is the amount of additional sleep these people get after taking the medication for 1 week, right? So we'll start with a baseline of 0, and the response is how much more sleep are you getting, right, because of taking that pill. If we're doing a one sample test, we're going to set our p-value threshold at 0.05. Let's move this out of the way. It looks like we want our power to be 90%, right? So we really don't want to miss something if it's truly going on because, hey, we paid a lot of money to develop this drug, right? So we want a power value of 0.9, and we're setting that p-value threshold at 0.05 just so we're still a rigorous study. The difference we expect to see, what we think would be helpful to people, is if they could actually get 1 extra hour of sleep. We're setting the bar low. This is our effect size, and we're saying that we really only want to detect an increase of 1 hour sleep. So say they go from sleeping 4 hours a night to 5 hours of sleep a night. And we know from our existing data that there's about a 2-hour standard deviation in how much people are sleeping. right, over the whole sample that we've taken. So if we were to go into jump, we're going to make our first foray into a different tab besides the Analyze tab. We're going to go into the Design of Experiments tab, and when we click that, we see a whole bunch of different options. Jump is actually pretty powerful in helping people design experiments as well and set up data sheets. We want to go to the Sample Size and Power option. So when we click on this, it's going to open a new window that has all sorts of different options. Remember, each different type of inferential test will have its own formula for calculating the required sample size for a given power. And what we were doing in this sleep aid example is we wanted to see if the sample we'd collected of people taking these pills, if that differed significantly from 0. We're assuming a population of 0. So we only have one sample of people, and we want to compare that to a population mean of 0 to see if they're getting at least 1 hour more than that 0, right? So we want to go into the one sample mean option. And when we come into this, it's going to ask for some information. It assumes that the p-value threshold that we want to use is 0.05, although we could change it. It wants to know what the standard deviation is that we expect for the population, and we said that was 2 hours. Extra parameters, don't worry about that. That gets into a little bit more complicated designs. What is the difference to detect? We said we were happy if we could detect a difference of 1 hour. Right? And the power that we said we wanted was 0.9, right? We still wanted to maintain power to make the study worthwhile. So when we enter all this information and hit 0, right, we can ask it to continue, and then it's going to plug in the number of observations. In this case, it's the number of people that have taken the drug, right? It's the number of observations we would need to be able to maintain this significance threshold so that we have less than a 5% chance of making a type 1 error, right? But also maintain our power so we have less than a 1% chance of making a type 2 error when all we're trying to detect is a difference of 1 and we have a standard deviation of 2. And we could do it the other way around. What if we had already done this test and we knew we only had 20 patients that had agreed to take this experimental drug, right? If we do that and then take out the power, right, you have to leave something empty for it to figure out. And now if we hit continue, it tells us the power of this test. So if we only have 20 individuals, it means that we only have a 56% chance of seeing a relationship when it truly exists, which means essentially that we have a 44% chance of missing a true difference, missing this 1 hour when it truly exists. So you can use this to go back and forth. What if it turns out that I really do only expect to see an hour increase, but the variability, man, these people are just all over the map, right? Maybe there are some people that sleep 1 hour and some people that sleep like 6 hours. Their variability is tremendous. But how many observations am I going to need now, considering that really the population is a lot more variable than I thought it was? Remember, again, the baseline was 44 observations. If my population becomes more variable and I increase that standard deviation, what it means is I now need 97 people to take this trial in order for me to say that there is a significant improvement of at least 1 hour that I expect. That formula will look a little bit different if we're doing a different type of analysis. We'll go right back down to the sample size and power analysis. But imagine now we're comparing two samples. This is what we would be doing in a t-test, right? We have two different populations and we'd like to know whether or not there's a significant difference between those. So now, imagine we have a standard deviation of 2. We'll just hold that constant. Imagine the difference that we expect to see is 1. So notice I'm holding everything the same as I was with the one sample test, but you're going to see the result is different because the analysis is different, right? Still want the same p-value, I still want the same power, 0.9, but if I now are comparing two groups, say one that took the pill and one that didn't take the pill, and I was just comparing the total sleep time between the two, now how many observations would I need? When I press continue, I can see that I would actually need about 171 people if I were trying to just randomly select from the population, give half of them the pill, and don't give the other half the pill. Now note down here that this sample size is really, for each group, is going to be divided by 2 because you're comparing two groups. So I'd need 171 total people, but divide that by 2 to find out how many you'd need to take the pill versus how many you'd be using as a control. And we could go on, but each different analysis is going to require a different formula to figure out that sample size. Let's try one more common power analysis. back up to design of experiments. Imagine that this time we have, I don't know, say 3 different groups that we're testing. We have the new drug we've come up with. We have the control group, just like we did with the 2 sample t-test. But imagine we also have another drug, maybe an existing one, that we would also like to try, and then another competing brand, right? So we have 4 different groups that we want to be comparing. This is a comparison of K, just refers to however many groups you want. So a K sample means comparison. Still wants my alpha, we'll keep it the same. Still wants my standard deviation, let's keep that the same, right? Still wants my power, my required power, and we're going to keep that at 0.9. But now it wants us to enter the means of each of these groups, what we expect the means would be. So it's going to calculate the effect size based on the means we enter here. So let's imagine that our control group sleeps about 4 hours a night, and that we expect with that difference of 1, our new group to sleep about 5 hours a night. Maybe the group before that, the old drug, maybe they slept 4.5 hours with the new drug, and then maybe the competing brand, maybe they sleep 6 hours, right? So we've just entered the means for each of these groups, and we can ask this now to tell us the sample size we would need to be able to detect these differences if they truly existed. We see that now we'd need about 108. So keep in mind that this 108 is the total number of observations. We would have to divide that by the number of groups we have to know how many observations we would need for each treatment, for each group, right? For the control, for our new drug, for the old drug, and for the competing brand drug. So let's just wrap up with a few final thoughts about power and hypothesis testing and significance, right? We know that we need to be conservative as statisticians. So we want to use that power, those power analysis, ahead of our actual experiments, right? We want to actually use them to help design our experiments. So hopefully this has been a really quick introduction to how the power of our analyses relates to that significance level and how we can try to control for those, or at least assess what our power for a given test might be. Okay, so we will be jumping right into applying all of this in our first inferential test starting next week.